Welcome back, everyone, to The Explainer. So glad you're here with us. Before we really get rolling, just a quick shout out. This educational content is brought to you by Forge College. Now, if you caught our previous lesson, Upgradeability Patterns Overview, you know we were kind of laying down all that theoretical groundwork for upgrading smart contracts. Well, today is moving day. We're grabbing all those upgradeability concepts, packing our bags, and officially moving from Ethereum over to Solana. We're going to drill down into the exact byte-by-byte blueprint you need to translate a classic Solidity proxy pattern right into its Rust and Anchor equivalent.
And, the second we start packing our bags for this move, we immediately slam into the single most pressing question every Ethereum dev asks, usually with a mild sense of panic when they transition to Solana. Where on earth did delegate call go? Seriously, we have absolutely all been there. You're looking for it, you're furiously scouring the docs, and it's just not there. No way around it. It's kind of the main technical antagonist of our explainer today, and figuring out how to survive without it is exactly what we're going to solve.
Okay, so here's our engineering blueprint for the next few minutes. We'll start with the delegate call dilemma, then move to mapping slots to bytes, building the anchor account, testing the binary layout, and wrap it all up with preparing for upgrades. Let's get right to it.
Section 1, the delegate call dilemma, leaving the EVM comfort zone. Let's look at this first major hurdle of moving our upgradeability mechanics over to the SVM. Now, to really grasp the SVM side, we kind of have to quickly rewind and remember how the EVM handles this. In Solidity, your proxies separate the logic, the implementation, from the state, which lives in storage slots. And they heavily rely on delegate call so that the implementation logic can just execute directly inside the proxy's own storage context. It's essentially like having a big shared closet. The EVM uses these massive 32-byte storage slots, and you basically just shove things into the closet. You'll loosely pack it in and just trust delegate call to rummage through and find what it needs later, purely because the logic and the proxy both agree on what the closet looks like.
But when we look at these two paradigms side by side, we see a massive shift. Since Solana literally doesn't have delegate call, that whole shove it in the closet packing method, that absolutely will not work. Under the SVM paradigm, we use cross-program invocation, or CPI for short, paired with a highly structured, super stable account layout. So if the EVM is at messy, loose closet, the SVM is like a custom-cut foam briefcase. Everything must have a precise, exact, non-shifting space. We're either storing state in an account that the implementation program accesses via CPI, or we're using a single program where the binary gets upgraded, but the account layout stays entirely 100% stable.
Moving on to Section 2, mapping slots to bytes, the translation dictionary. Layout compatibility is literally the single most critical constraint for this entire blueprint. Let's look at this literal blueprint mapping. It shows how successive Solidity slots translate perfectly into an anchor account struct with a completely stable binary layout. Let's walk through this together. Say in Solidity slot 0, you have an address. In Anchor, that maps to our admin field as a pub key, which takes up exactly 32 bytes. Simple enough, right? Next, Solidity slot 1 might hold a UN64 counter. Over in Anchor, that becomes a U64, taking up exactly 8 bytes. Finally, down in slot 2, you've got a Boolean initialized flag. In Anchor, that's just a bool, which takes up exactly 1 byte. But wait, plus something incredibly important here, padding. This is an absolutely crucial point, explicit padding. In Solidity, smaller types just get padded into those big 32-byte slots automatically for you, but Anchor and Borscht serialize fields strictly in order with minimal padding. So to force a stable, highly predictable binary layout in Anchor, explicit padding is strictly required to mimic those EVM slot boundaries. If you skip this, you risk totally corrupting your state across different program implementations. You literally have to manually tell Anchor, hey, leave some empty space right here, just so the byte offsets align perfectly. Section 3, building the Anchor account, precision engineering. Let's pull up the actual Rust code and see how we construct our proxy state struct based on that canonical mapping. Whenever you write this struct, you are defining a binary layout. That's the exact, predictable byte-by-byte sequence of serialized data in memory. And because of this, you've got to control your field order with an iron fist. You have to use fixed-size types, things like pubkey, U64, or fixed arrays. You absolutely must avoid dynamic collections like a vec of t for upgradable state, unless, of course, you've designed a really explicit growth strategy. If the size of a field can just change dynamically, well, your entire custom-cut foam briefcase just falls apart, and that rock-solid logic structure you relied on back in Solidity is gone. Which brings us to a very magic number, 56. When you allocate space for this account in your initialization instruction, you need exactly 56 bytes. Why 56? Well, let's do the math. Our map state is 48 bytes total, 32 for the admin pub key, 8 for the counter, 1 for the Boolean, and then 7 bytes of that explicit padding to round it out to a nice clean 48. But we also have to pay a little bit of a tax to Anchor. Anchor mandates an 8-byte discriminator at the very beginning of the account, just to securely identify the account type. So 8 bytes for the discriminator plus 48 bytes for our mapped state gives us exactly 56 bytes of total space allocation, the whole shebang.
Section 4, testing the binary layout. Trust but verify. Because trust me, guessing based on high-level types is a fast track to deploying absolute garbage to mainnet. So here is the exact chronological verification checklist every developer must follow to ensure their struct perfectly matches the blueprint. First, compile and run your Anchor test using a local validator. Just make sure the build actually succeeds, right? Second, confirm your logical initializer values. Your test should write to the account and then assert that the admin public key matches and the counter actually starts at 0. And third, inspect the raw bytes and offsets. This right here is the definitive, undeniable proof of layout compatibility.
Doing this means looking way past those high-level JavaScript or Rust types and diving headfirst into the raw hex. If you did everything right, your 8-byte Anchor discriminator takes up bytes 0 through 7. Your 32-byte admin pub key takes up offsets 8 through 39. And then there's that beautiful moment of developer anxiety, where you're manually decoding raw hex bytes just to find your little Indian U64 counter sitting perfectly in its designated slot at offsets 40 through 47. Wait, actually, hold on. Looking at the text here, it says offsets 32 to 40. Let's actually re-verify that mapping mentally. The 8-byte discriminator is offsets 0 to 7, right? The admin pub key is 32 bytes taking offsets 8 to 39. So the counter actually does start at offset 40, going to 47. Ah, see? The offset math is incredibly precise, and it's so easy to get tripped up, which is exactly why manually checking these offsets yourself is absolutely crucial. The sheer triumph of seeing that exact byte placement confirms not just logical equality, but your exact flawless binary mapping.
Section 5, preparing for upgrades. Key takeaways. Let's pull all these threads together to wrap up our layout mapping and set our sights on the actual deployment workflows. Ultimately, it all boils down to these core migration rules. When you're migrating proxy patterns, you have got to control your byte sizes. Match your field order exactly to what it was. Stick to those fixed size types. Always include your explicit padding. Calculate your space allocation accurately. Don't forget that 8-byte Anchor discriminator tax. And finally, always back it up with binary level confirmation tests.
So, we've successfully laid out the perfectly mapped account. Next up in this module, we'll be tackling Anchor upgrade flows and practices. We're going to take this rock-solid layout and push it through real, safe code upgrade procedures on Solana. We want to ensure existing accounts deserialize correctly, even after a massive program upgrade.
Before we go, I want to leave you with this somewhat terrifying thought. What happens to your user's state if even a single byte is misaligned during your next upgrade? The stakes of binary alignment are literally sky high. Mastering this mapping is quite simply the difference between a seamless upgrade and irreversible state corruption. Thank you so much for hanging out with me for this explainer. I highly encourage all of you to head over to forge.college to dive even deeper into this material and really master these vital Web3 topics. See you in the next one.